Okay, so let us see our first example of a non-commutative tree. So this is the sixth example. Let R be the set of all symbols alpha 11 E11 plus alpha 12 E12 plus alpha 21 E21 plus alpha 22 E22. This can be written more compactly using the summation notation. Summation alpha ij eij, where I and j are varying from 1 to 2 independent of each other, where the alpha ij's are rational numbers. Okay, so R is the set of all such symbols where these alpha ij's are rational numbers. Note that we are not saying anything about these eij's. They don't have any separate meaning outside of this symbol. They are just part of the symbol, and just like that, these plus signs are not ordinary addition. They just start to connect the parts of this symbol together. These are the four parts. So separately they don't have any meaning as of now. So maybe later on we may be able to assign some meaning to them, but that will come later. So R is the set of such formal symbols where these numbers, these are rational numbers, the alpha ij's. We may call them components of the symbol, just like a vector has components, something like that. Now, since this is a set of formal symbols, everything we do on this set, it has to be defined. So the first thing, our aim is to make this set R a ring. So first of all, we define equality of two such symbols. So we declare two such symbols summation alpha ij eij and summation beta ij eij to be equal that is if and only if alpha ij is equal to beta ij for all I and j varying from 1 to 2. This means I can take the value 1 and 2. J also can take the value 1 and 2 independent of I. So this definition of equality is very natural. It's just like how two vectors or two three-dimensional vectors are equal, just like that. Now after this we define the operations. Next we define an addition and a multiplication in R as follows. So here are the definitions. Addition is quite easy. We just add the corresponding components of two such symbols. Alpha ij, eij, plus summation beta ij, eij. This is defined to be equal to summation alpha ij plus beta ij eij. So the sum of two such symbols is again another such symbol where the components are sum of the components, corresponding components. Then we define multiplication. Summation alpha ij eij times summation beta ij eij is defined to be equal to again another such symbol summation gamma ij eij where gamma ij is defined to be this quantity alpha I1 beta 1j plus alpha I2 beta 2j. Okay, for all I and j. Now let us pause and take a look at these definitions. There is only one thing I want to draw your attention to. You see, we have a plus sign here and a plus sign here. Keep in mind that these are two different operations. This is the plus we are defining in the set R. That is, it's a plus between two such symbols, two elements in R. However, this plus is ordinary addition of two rational numbers. Although we are using the same symbol for these two operations, we have to keep in mind that there is a distinction. They are basically not the same thing, they are different things. We use the same symbol because they behave similarly algebraically. Each one of them is commutative. I mean, we will prove that this is commutative. This operation that we have defined here, it is associative. Same is the case with ordinary addition of rational numbers. That's why we use the same symbol. Just like that, here this multiplication is not ordinary multiplication. These things have to be kept in mind. Okay, now I am going to make a statement, and the proof of that, although it's straightforward, is somewhat lengthy, and that I will leave to you. Namely, the statement that under these two operations, R is a non-commutative ring with unit elements. So let me just first write the statement and then I will say something. It can be shown that under these operations R is a non-commutative ring with unit element. Okay, now the proof of this is left to you. It's not very difficult. You just have to take the symbols and verify all the properties one by one. For example, we can at once verify the first property, namely that if we add two such symbols, then the result is again in R. If you recall the axioms of a ring, the result must again be in R. So by definition, two such symbols give, if we add them up, they give us this. Now, this is again one such symbol where these components are rational numbers. Why? Because sum of two rational numbers is again a rational number. That result we are using here. So, this belongs to R. So, the first axiom is verified. Similarly, the other axioms can also be verified. Just a word, you will need the zero element. So zero element is just this one, 0E11 plus 0E12 plus 0E21 plus 0E22. Okay, this you can see from the definition of addition, this is going to be the zero element. Also, for this element, say, we need an additive inverse, right? So for that, the additive for this particular element, the additive inverse is just this. Take the negatives of all the components. E11 minus alpha 12, E12 minus alpha 21, E21 minus alpha 22, E22. Okay, but you have to be careful with the multiplication, because the multiplication is not as natural as the addition. Although it is based on some rules, we will understand the reason for this strange multiplication later on in this book, okay, when we study matrices and linear transformations. Anyway, so this part, with these things, you can show that R is a ring. Why is it? Okay, what is the unit element? So let me just tell you what the unit element is. It's left to you to verify that this is the unit element. The reason that I am using these symbols 0 and 1 is now clear. These symbols are not ordinary numbers 0 and 1. They are 0 element and unit element in the ring R. Okay, so here the unit element will be this. 1E11 plus 0E12 plus 0E21 plus 1E22. You can verify that if you multiply any element with this, you are going to get this element back in any way, either this times 1 or 1 times this, using this definition of multiplication. So this much can be verified by you. So R now is or can be shown to be a ring with unit element. But what about non-commutative? That's the main point, right? Because so far we have seen only commutative rings. So let us now look at that. How is this ring non-commutative? Okay, for that, let us produce two elements which do not commute. That's enough for showing non-commutativity. Let's take two symbols and multiply them. And the two symbols are this. 0E11 plus 1E12 plus 0E21 plus 0E22. This is one element dot 0E11 plus 0E12 plus 1E21 1 plus 0E 2. Now we have to apply the definition, but what does the definition say? Okay, so to make sense of that, temporarily let us call these things, these components, by using these symbols like what we have in this element, so that we can understand the product. Alpha 2, like that, these 0, 0, 1, 0, these are beta 1, 1, beta 1, 2, beta 2, 1 and beta 2, 2. Now we apply the definition, just like how it has been defined. So this will be equal to, again a symbol like that. So we will have a component for E11. We may call it coefficient of E11, and that will be alpha 1, 1, beta 1, 1 plus alpha 1, 2, beta 2, 1, E11 plus, then for E12, gamma 1, 2. So alpha 1, 1, beta 1, 2 plus alpha 1, 2, beta 2, 2, E12. Let me first write it down and then we will see how it is what we are supposed to write. Then alpha 2, 1, beta 1, 1 plus alpha 2, 2, beta 2, 1, E21 plus alpha 2, 1, beta 1, 2 plus alpha 2, 2, beta 2, 2, E22. Okay. So what is gamma ij? In gamma ij, we have the I and j fixed. You may call this I and j outer coefficient, outer suffixes, if you want, because they are appearing, if you see, in a sense they are outer, whereas these are inner suffixes. Temporarily let us just call them. The outer suffixes stay I and j, but the inner suffixes change. They take the two values 1 and 2 and we add the terms, corresponding terms. So here the outer suffixes are determined by these 1, 1. So here you see 1, 1, 1, 1. The inner suffixes are changing from 1 to 2, 1, 1, 2, 2. They are the same. Okay, so here, just like that, here the outer suffixes are 1 and 2. So here we have 1 and 2, 1 and 2. The inner suffixes are changing from 1 to 2. Like this, like that, this one also. 2, 1, 2, 1, 1, 1, 2, 2. And this is 2, 2. Okay, so that is the multiplication. Now we recognize these values. First of all, you see alpha 1, 1, this is 0, so this term is 0. Then alpha 1, 2, beta 2, 1. Alpha 1, 2 is 1, beta 2, 1 is 1. So this is 1. Like that, here alpha 1, 1 is 0, so this term is 0. And beta 2, 2 is 0, so this is 0. Beta 1, 1 is 0. Alpha 2, 2 is 0. Here alpha 2, 1 is 0 and alpha 2, 2 is 0. So the thing now simplifies to 1 E11 plus 0 E12 plus 0 E21 plus 0 E22. So that's how, using the definition of multiplication, we have calculated this product. Now we are going to calculate the other one, switching the order. So 0e11 plus 0e12 plus 1e21 plus 0e22 dot 0e11 plus 1e12 plus 0e21 plus 0e22. So here, okay, here also now to keep things in track, let us now temporarily call them alpha 1. I know it's not the same thing, but once this calculation is over, this step actually is not needed, right? We have got what we wanted. So let us now call again, let us call these things now alpha and these as beta, so that we can apply the formula. Since the formula is slightly complicated, we have to be careful in applying it. That's why we are writing these things. Alpha 21, alpha 22. But once we understand actually what is going on inside the formula, then it will be much easier to calculate that. We are going to get to that. Beta 12, beta 21, beta 22. So again, let's just take a look at this. In this case, alpha 11 is 0. Okay, so this term is 0. Then alpha 12 is also 0. So here, now that we have already carried out the calculation in detail once, here we can be somewhat sketchy. So the first coefficient is 0. Then for the second one, alpha 11, beta 12. Alpha 11 is 0, so this is 0. Then alpha 12, beta 22. Alpha 12 is 0, so again 0. 0e12. Then we come to this one. Alpha 21, beta 11. Alpha 21 is 1, beta 11 is 0, so this is again 0. And then alpha 22, beta 21. Alpha 22 is 0, so this term also has the 0 coefficient. Finally, alpha 21, beta 12. Alpha 21 is 1, beta 12 is also 1, so here we have a 1. And alpha 22, beta 22, they are 0, so this is 1. So you see that these two things are not equal. Clearly, because here the coefficient of E11 is 1, here the coefficient of E22 is 1. So that's why these two terms do not commute, and hence the ring is non-commutative. Okay, so it's a non-commutative ring with unit element. Let us now come to the question of making things easier, because this is really cumbersome, right? So we can make things easier like this. Okay, so now we are assuming that we have the ring structure. Now let us define some symbols. Define what should I call this? If I use the same symbol, you will get confused. So let me use a slightly different symbol. Define alpha 1, or I can use the same symbol, right? Okay. Define E11 star to be this element 1E11 plus 0E12 plus 0E21 plus 0E22. E12 star to be this element 0E11 plus 1E12 plus 0E21 plus 0E22. Like that, E21 star is, looking at the pattern, you now get what it will be. It will have all the coefficients 0 except the one of E21, that will be 1. And then E22 star E22. Okay, so the calculation that we have carried out right now, just before this, that is just this E12 star dot E21 star. One of the products was this and the other one was this, the other product, switching the order, E12 star. This turns out to be equal to E11 star. If you go back to that calculation and see, this turns out to be equal to E22 star, and they are different. Okay. Now, if we take a general element of the ring R, that is this one, alpha 11 E11 plus alpha 12 E12 plus alpha 21 E21 plus alpha 22 E22, and if we define a new operation, okay, now we are going outside the ring and we are defining a new operation. Actually, we should not do this, but for the sake of making this calculation simple, we are doing it. It's like multiplying a vector by a scalar. If you multiply a vector like this, like your ordinary vector in 3D, say, a vector like this by a scalar, say 2, what do? You multiply all the components by that scalar. So this becomes 4i cap plus 6j cap plus 8k cap. We are going to define a similar operation on R. By that, what we mean is this. If I multiply this symbol, now it's not a vector, we are not saying anything like that. A ring element by any rational number, say R. For us, that means this. Oh, sorry. Plus. That is, we are multiplying every such rational number by this one. Alpha 21 E21 plus alpha 22 R alpha 22 E22. The point is that in doing so, we ultimately get again a symbol of that type, that is again an element in R. Okay, why am I saying these things? I am saying these things because I can reinterpret this symbol slightly differently. Now, look at this. Alpha 11 E11 star plus alpha 12 E12 star plus alpha 21 E21 star plus alpha 22 E22 star. Okay, what is the meaning of this? These are these elements in R, in the ring R, and this multiplication, the multiplication where I am multiplying this ring element by this rational number, is the one that I have defined right now, like multiplying a vector by a scalar, that thing. Okay, so ultimately this product again gives me a ring element, like that. All these are ring elements where I am multiplying the ring elements, this particular ring elements, by some rational numbers. Okay, and this addition is this addition that we have in R. Then this is meaningful. Inside R, this calculation is meaningful. But what is the result of this? If you look at these symbols and multiply that, for example, this one by alpha 11, what will you get? You are going to multiply each component by alpha 11. So alpha 11 E11 plus 0 E12 plus 0 E21 plus 0 E22. This is this one plus, like that. I am going to multiply this by alpha 12. 0 E11 plus alpha 12 E12 plus 0 E21 plus 0 E22. Similarly, for the third one, I have 0 E11 plus 0 E12 plus alpha 21 E21 plus 0 E22 plus there is one more. So the fourth one is 0 E11 plus 0 E12 plus 0 E21 plus alpha 22 E22. Now this is an addition in R of 4 ring elements. If we actually carry out the addition, what do we get? We get nothing but this alpha 11 E11, because we have to add the corresponding coefficients, right? Alpha 11 0 0 0, that gives me alpha 11 E11. So like that, alpha 12 E12 plus alpha 21 E21 plus alpha 22 E22. Okay, so now you look at this ring element and this calculation, I mean this should I say linear combination, okay, of ring elements and some rational numbers. So you can see that these E11s that we have in these symbols, which otherwise don't have any meaning of their own, they can now be reinterpreted as elements in R itself, these particular elements. And this is the reason we use this plus sign, and that is why we write the general element of this ring like this, because ultimately they turn out to be something like this, which matches the form of the element. This tells you why these symbols look like this. But there is more. Do you see these calculations? These calculations actually suggest a general thing, which is this: Eij star dot EKL star, where I, J and K and L, all of them independent of one another, can take the values 1 and 2. This is equal to EIL star if j is equal to k and 0 means the okay, what is 0? 0 means the zero element in the ring. If j is not equal to k, this can be proved. Okay. Now, because we can express a general element like this, like a structure, a combination in the ring. So the multiplication that we carried out using the formula that has been defined for us can now be simply carried out using this and just ordinary algebra that we have already used, we have been using. So what I'm trying to say is this: if I now take two elements like this in the ring, A equal to, say, what he has taken, Herstein, E11, 1, actually I should write 1 E11 plus 0 E12 plus minus 1 E21 plus 1 E22. This is one element, okay, and the other element is this 0 E11 plus, is it 1 2? Yes, 3 E12 plus 0 E21 plus 1 E22, and we want to say multiply this, but now we don't have to use the definition. Why? Because I can express A